Alright, let's take a look at today's lesson. So today we are working on Polar Day 1. I am so excited. I'm sure you are too. So we're going to start out a little bit slow. We're going to just look at some review from last year. The review things are on the left side of the slide. And the newer things, the calculus things, are on the right side. Will be the new things. We're looking at the slope of the tangent line and arc length. So those are our goals for today. So let's start with our older stuff. So just a reminder, when we are working with points in polar form, that the point is r, which is the r is the distance from the pole or the origin. So if you look over here at this example, it would be this distance right here. I think of it as the number of rings, actually, the number of rings away from the origin or the pole. And then, of course, theta is our angle measure. The angle measure is always counterclockwise here, just like regular trig stuff. So just a reminder on how we would plot this point. If we go to 5 pi over 3, which is indicated right here, we rotate to 5 pi over 3, and then we go out 3 rings. That would be this point. Now, what if that was a negative 3? Do you remember from last year what would happen if that was a negative 3? We would just shoot across the other side, right? It would just shoot right across the other side, 3 rings on the other side, and this is the point that we'd be looking at. So just some reminders about polar graphing. The other things from last year, we learned these 4 formulas, which are pretty important to us. These 4 formulas right here allow us to go back and forth between polar and rectangular form, and back and forth. So that's pretty important. The formulas, these 2 right here, are really pretty critical for us. They develop the relationship between polar and x and y. So there will be times when we're asked some questions that have polar equations, and we're asked, you know, for the x coordinate or the y coordinate, and you're thinking, what? I don't have any x's and y's. And this is where we go to. These are the equations that we go to. These are the relationship between x and polar, x and y and polar. And we're also going to be looking at graphing polar curves. That's going to be important to us in the next few lessons. And in day 2 and day 3, we spent a lot of time on graphing, or basically calculating the area inside a polar curve or inside parts of a polar curve. So being able to graph this, here's the basic standard ones by hand, are going to be pretty important to us. On the daily work, the first questions I do ask what kind, the name it. Don't stress about that. You're not going to be asked the name of one on the AP test, and I'm not going to ask you the name of one. I just thought it was fun facts, just some fun facts. What is this one called? Alright, and then let's start on the new stuff. The new stuff would be our calculus stuff. Just like when we were dealing with parametrics. Okay, I want to spend a little bit of time talking about dy dx. So dy dx is the slope of the tangent line, period, regardless of what mode you're in. Whether we're in function mode, it's dy dx. If we're in parametric mode, it's dy dx. Recall that that formula in parametrics for dy dx was a little different. It was dy dt over dx dt. I recall that, but it's still dy dx. We have a separate formula in polar for dy dx. Again, the meaning of dy dx is the slope of the tangent line. That's basically what we use it for, just the slope of the tangent line. So it has its own formula, and I actually don't memorize it. I have, to be honest, some issues keeping the cosines and sines straight. Where do they go? Where's negative? Where's positive? So what I do, and it just takes just a few seconds, is I generate it every time. We're going to generate it from these 2 equations, and we're going to use the product rule. Okay, so we're going to generate this. I'm going to show you how to generate it. It's your choice whether you decide to memorize it or not. Alright, so we have a fraction here. And in the numerator, we're going to do dy d theta. So over here, we've got our y. We're going to do fg plus fg. First things first, second things second. Right, it's the product rule. This is my first function. This is my second one. So we take the derivative of the first one, r, which is 1, and it's not a theta, so we tag it 1 dr d theta. Then we copy paste the second one, sine, plus We copy paste the first thing, r, and then we take the derivative of sine. The derivative of sine is cosine, and this happens to be theta, and we're doing this with respect to theta, so no tagging is required on that last derivative. And that's our numerator. Now let's work on our denominator. On our denominator, we're going to be doing the same thing, but to this equation. So again, this is my first function, this is my second one. So we take the derivative of the first one, r, which is 1. It's not a theta, so we have to tag it. It's 1 dr d theta. Copy paste the cosine. And plus, I would put a plus, but I'm just going to hold off on a second because of the derivative of cosine we know is negative sine. So let's just hold off for just a second. Then I copy paste the first thing and take the derivative of cosine, which is negative sine. And again, the cosine has a theta, and we're doing the derivative with respect to theta, so no need to tag. Now this is the derivative. This is the derivative that you have two choices. You can either memorize it as is, so this is our dy dx derivative for polar, or you can generate it just like I did each time. So up to you. What I found myself having trouble remembering, like where was the sine and where was the cosine, which ones were cosines, which ones were sines, where was the plus, where was the minus. I thought, I'm just going to generate it every time. I don't want to have to try to memorize that, and it just takes just a few seconds. So that's our new formula for tangent line, for polar. Now, yes, this is our third arc length formula. You're probably so excited. You had two of them, you didn't have enough, now you need a third one? Yes. So let's remind ourselves the other two. If you recall, for functions, it was the integral from a to b, square root of 1 plus f prime squared, right? That's what it was. That was for functions. Then we just finished the parametric arc length. The parametric arc length was from, a to b, still square root, but it was dx dt squared plus dy dt squared. Okay, so now that takes us to our polar arc length. A little bit different. It's still got a root like the other two. These are angle measures. The bounds are angle measures. This is alpha and beta. Those are angle measures. And we square root, then we do r squared, and r is the equation, the r equal equation. Then we do dr d theta squared. So that's our new polar arc length formula. So now we have 3. Oh, how exciting. So many options for formula quizzes, right? Oh, there we go. Okay, so let's move to the next page so that we can work some problems. Okay. So the problems along the top are problems from the old stuff. And then our new things are here, where we're going to do dy dx, and here for arc length. So let's start with the older stuff first. They want us to find the rectangular coordinates for 7 and 2 pi over 3. So this is my r, and that's my theta. Okay, so looking at that. Let's see, so we're going to use our x equal equation and our y equal equation. That would simply be the easiest. So x equals, remember it's r, so 7 cosine of theta, 2 pi over 3. And so that's going to be 7, let's see, 2 pi over 3, let's see where that was. 2 pi over 3, 4 pi over 6, what's up here? Cosine is shorter, so it's the 1/2. And it's on the negative side, so it's times negative 1/2, right? So my x coordinate is negative 7/2. Now let's work on the y coordinate. That's going to be 7, which is r times sine of theta, sine of 2 pi over 3. So let's think about that same location. It's tall and positive, so that would be 7 times root 3 over 2, which is 7 root 3 over 2. So our new coordinate, our rectangular coordinate, is negative 7/2 and 7 root 3 over 2. Now just a reminder, when we are finding this coordinate point, we are really looking at the exact same spot. We are mapped to the same location on our grid, whether we're in polar or rectangular form. So if I were able to look at my point, I were able to go over 7.5 and up. That location is also represented by this in polar form. So this point in polar form and this point in rectangular form map to the exact same place, just so we're clear. They're the same location. All right, now we're going to go the other way. We're going to, this is our x and this is our y. We're going to go to polar coordinates. So we're going to use the other two formulas, the x squared plus y squared equals r squared. So 3 squared plus 4 squared equals r squared. So what is that, 9 and 16, so 16 is r squared. So r could be a plus or minus 4. Oops, that's 25. 9 and 16 is 25, not 16. So it could be plus or minus 5. It's 25 plus or minus 5. Remember, it could be plus or minus. It just kind of depends on where we want to go and what our angle measure is going to turn out to be. So it could be either one. So let's just keep that in mind. So the other formula is tangent theta equals y over x, so 4 over 3. And if you were wanting to find an actual, approximate angle measure, we would need a calculator for this. So I used my calculator and I did arctangent of 4/3, and I got that theta is 0.927. Okay, so let's kind of think this through and make sure we're going to match these up properly. I need to be 0.34 is in the first quadrant, right? Somewhere, maybe over here, somewhere there. So that's 3, 4. So the ones that I pick out, the angle measure and the R measure that I pick out, better land me in the first quadrant, or I've chosen incorrectly. So 0.92, let's think about that. We know this is 0 and this is 3.14. So this is, a little bit more than 1.5. So 0.9 would be in the first quadrant, so that's good. That means we need to use a positive R value. I mean, we really don't have a choice if we're going to use 0.927. So we need to use the positive R value. So let's do that. So positive R value of 5, and then our angle measure is 0.927. And there's our point. This again would map to the same place that this one does, just in a different coordinate grid. All right, so hopefully that's good. Let's go to our next ones. So we want to find the rectangular coordinates. And so this says rectangular coordinates. That really confuses students. It's like, what? Coordinates? I'm thinking of coordinate points. What is it talking about? That's just another way to say, put it in Cartesian form. Why they say rectangular coordinates, I don't know, but it's a thing. It's just a thing. They're going to say that regardless of whether it's a point or it's an equation. See how they said over here, polar coordinates? Yeah, same kind of thing. We just need to find this particular equation in rectangular or polar form depending on what they're asking for. So let's do that. From polar to rectangular, I think can be a little bit more challenging. So keep in mind we need that x equals r cosine, y equals r sine. We really need cosine and sine here, and I have secant and tangent. So the very first thing that I would do is I would rewrite it. I would use a reciprocal property and a quotient property. So 1 over cosine times tangent, that's sine over cosine. Now I don't particularly like to work with fractions in this way, so I would multiply both sides by cosine squared. So I would get r cosine squared equals sine. Now if I squared both sides, I would certainly, make some progress with the r's, but that really isn't going to help the right side. So I'm going to do a technique that some students just really don't like. I'm not really sure why. We're going to multiply through by r. It's okay to do that, not a problem. Multiply the whole equation through by r. So I'm going to get r squared cosine squared equals r sine theta. And so we know from our formulas, we know from, let's start with exponent stuff. We know r squared cosine squared is the same thing as r cosine times r cosine, which would be x times x, right? That's what we know. And we know r sine is y. So our equation becomes y equals x squared. So this is a parabola. Now just so we're clear, this parabola in rectangular form is going to look the same as this weird secant tangent thing in polar form. It's going to map to the same place. Okay? So now let's go the other way. Let's find the polar coordinates from rectangular coordinates. This I think is a little easier. We're just going to replace x with r cosine. So x is r cosine theta and y is r sine theta equals 4. Okay, great. we always want to solve for r, that's our thing, or r squared. We can leave it as r squared, it's okay. So I'm going to pull out those, that's r times r would give me r squared. Then I'm going to divide that by all the rest of that stuff. So what, 9 cosine sine. Now we normally, if we can help it, we normally don't like leaving these polars in fraction form. So if there's a way to make it non-fractional, we would do that, and there is. We know that, well, we got 4/9. We know that cosine, 1 over cosine is secant, and we know that 1 over sine is cosecant. So this is how we could leave it. And if it really bothers you to have r squared, you can certainly square root both sides and do plus minus radical, it's fine. But it's also fine to leave it as r squared. Okay? Alright, so the last part of the old material is to graph. And I know it's kind of hard to see with this. It's asking us to graph 3 times 1, so r equals 3 times 1 plus sine. That's what it's asking us to graph. So let me clean this up just a little bit. Okay. Alright, so in order to do that, what I would want to do is distribute the 3. I don't really want to deal with it like that. So r would be 3 plus 3 sine. Okay. So my favorite way to graph is to use the Cartesian graph. I use that as my t-chart and I plot points from my Cartesian graph. That's just, to me, the easiest thing to do. So that's what I'm going to do. You can certainly do this however you want. So my amplitude is up 3. So my sinusoidal axis is here at 3. Excuse me, my shift. I have a shift up 3, and so my sinusoidal axis is at 3. My amplitude happens to be also 3, so we would go 3 up and 3 down. We're going to use our same 4 points that we typically use, all the quadrantal points, pi over 2, pi, 3 pi over 2, and 2 pi. And so now, let's see, sine we know starts at its sinusoidal axis and then goes up, then comes down, then goes down, and then goes back up. So it kind of looks like this. Okay, so now I'm going to use these values. This would be like my theta values, and these would be like my r values. Okay, so I'm going to go to theta measure of 0 and an r value of 2, and I'm going to plot my point. Okay, there is 0, my theta measure of 0, my r measure of 2. Then when I get to pi over 2, I'm at, what, 6? Oh, no, that's 3. Let's fix that little guy up. Okay, that's a 3, 1, 2, 3, so it's right here. And then the other one, pi over 2 is at 6. Puts us up here. And we always want to connect these by curves. Is it possible to have straight lines with polar curves? Yes, that's quite unusual. It would be quite unusual. The majority of the time they're curves. And we kind of want to make the curves just kind of a little plump. You know, we don't want to make them like real flat, because it's just going to be helpful for us when we're working with area to just kind of maybe even try to exaggerate it just a little bit. So we want to come, and that's probably not even plump enough. Maybe you can make yours plumper than that. Alright, so we go back to pi and we're at 3. So here we are at pi. We're going to move to 3. And 3 pi over 2, we're at 0. Now, there are a lot of students that want to draw a straight line here. Please don't do that. It's not a straight line. If you follow this path, going from, we were at theta, excuse me, at pi, notice how it starts at a ring of 3, then it goes down to a ring of 2, and then a ring of 1, and then a ring of 0. So it's actually inside the third quadrant, just changing, going from a ring of 3 down to, 2, and then to 1, and then to 0. Okay, that's where it ends up. Then at 2 pi, we are back at 3. Okay, so there's our graph. All right, great. Okay, good. So that's all the old stuff. Now let's move to the newer stuff. So, alright, so this, we'll just start with this example right here. Find dy dx and the slope of the graph of the polar curve at the given value of theta. Alright, well, what do we do? So, yes, we get to use our new derivative formula. I know you're so excited. let's create it from scratch. Why don't we? So dy dx equals. So the top would be r sine, right? The derivative of r is dr d theta. Copy paste the sine, plus, copy paste the r, then the derivative of sine is cosine. There's our numerator. Denominator is that's the y one, right? Y equals r sine, okay? Excuse me, it's the bottom one, r cosine. X equals r cosine. We just did the y equals r sine. Now let's do the x equals r cosine. So let's see, the derivative of r is 1 dr d theta. Copy paste the cosine. I'm going to leave that blank because I know I'm going to copy paste the r, and the derivative of cosine is negative sine, so that makes it negative. So there's our formula. Yay! Now let's use our formula. Alright, so we need a little bit of room. I know you're just surprised about that. So dy dx equals dr d theta. Well, this is our r equals, so let's find dr d theta. So the derivative of 3 is 0. The derivative of 2 sine is 2 cosine. Alright, so our dr d theta is 2 cosine. Then we're supposed to copy down sine. Plus. Then r is this. R is this formula. So 3 plus 2 sine, copy paste cosine. And that's our numerator. Okay, now let's look at our denominator. We have our dr d theta again, which hasn't changed. It's still 2 cosine. Copy paste the cosine, minus r, which is our formula, 3 plus 2 sine, copy paste sine. And that's our formula. Yay! So, we could do some fun stuff with it. We could condense it, or we could stop. We could just plug pi over 6 in right now, but I have to plug pi over 6 in 8 times. 4 times in the numerator, 4 times the denominator, which I could do, right? We could do that. That's fine. If we wanted to, and we love to do trig, I do. If we wanted to do some trig, then we could do some properties. Look at this little guy right here, 2 cosine sine. You know what that is, remember? Oh, yes, I bet you do. It's 2 sine 2 theta, right? That's a double angle for sine. And so we could mess with it and move it around, distribute combined like terms, and turn things into double angles. And just for fun, of course, I would do that. So just for fun, this is what you would get if you did that. If you went ahead and simplified that, which again, you don't have to. But if you did, you would get 2 sine 2 theta plus 3 cosine in the numerator. In the denominator, you would get 2 cosine 2 theta, oh, double angle for cosine, minus 3 sine theta. And now that makes me happier because then I only have to plug pi over 6 in 4 times. Numbers is not my strength. I kind of save that for, to be real careful with that. So I would plug in pi over 6. And so we know how to plug numbers in and calculate. I'm not going to take the time to do all that. I will tell you though, when you've plugged in pi over 6 and you've done your derivative, you're going to get dy dx at pi over 6 is negative 5 root 3. Now what did that give us? That is giving us the slope of the tangent line to the polar curve at pi over 6. If we were wanting to write the tangent line, we would need this value for our slope. That's what it gives us. Okay, so there's dy dx for polar. Then our last one, we're going to look at arc length, and we get to use our new arc length formula. We're so excited. So the length of the arc we're going from 0 to 2 pi. Well, that's pretty easy. So our arc length is from 0 to 2 pi, square root of, it's r squared, so 2 minus 2 cosine theta squared, r squared plus, then it's dr d theta squared. So let's do our little dr d theta over here, just some little scratch work. So the derivative of 2 is nothing. The derivative of negative 2 cosine would be, a positive 2 sine. So we have 2 sine theta squared d theta. And that would give us our arc length. We would just, if it asks for the actual arc length, let's just go ahead and put that in our calculator. You can do that at the same time that I am. I encourage you not to distribute and combine like terms. Just let it be, like, just input it just like that. Okay, make sure your mode is in radian mode. Okay, it's in radian mode, so we do math 9. We're going from 0 to 2 pi. And then we've got square root of. So we'll do our parentheses, 2 minus 2 cosine. And then let's close our parentheses and square it. Plus, open our parentheses again, 2 sine. Close the parentheses and square that. And then type in your dx. And let's see what we get. Oh, wow. Can you believe it? We get 16. Out of that craziness, yes, we get 16. And that is the arc length, or the length of the curve, starting from 0 and going to 2 pi. All right. How are we? Is everybody okay? All right, great.